Welcome to Advanced Reverse Engineering. There's homework. The homework is to write a little piece of assembly that prints a string a given number of times. You'll need to use puts and a to I from the C standard library to make this work. If you have an error, print out an error message starting with the text error. Name your file hello.asm. Should be fairly simple. You can get command line arguments off the stack. argc will be an EDI. argv will be an RSI. So don't mess with the stack at all. Okay. You should pay attention to callee versus caller saved registers. You should save the ones you need to save. If you want to use a callee saved register, you need to save it and then restore it at the end. If you are calling something like a to I, you need to save any caller saved registers, because you're the caller then, and restore them after that call. You should assume that a to I will mess up any of those caller saved registers. Let's talk about tools. We're going to skip this. Let's get to dynamic linking. So just a quick refresher. The assembler knows the distance between elements in the same section, but it doesn't know the distance between elements in different sections, how they relate. It doesn't know how the sections are going to be laid out. It doesn't know any absolute runtime addresses, and it doesn't know how to reach out to things that are outside of the file itself, right? Like things in shared libraries. Someone else has to fix that, so it creates relocations for those. The linker actually lays the sections out in the file and creates things like the GOT. So it knows how things within an ELF file relate to each other. So it knows like distances within an ELF file. So it would know the distance between, say, part of the text and some element in data or BSS. Okay? Knows those, but what it doesn't know is the absolute address at runtime. Neither the assembler nor the linker knows the runtime address of the program because it's going to get moved around and it might even be randomized. Those have to be resolved by the dynamic linker, or the program loader. And they're dynamic relocations, or sometimes called runtime relocations. I'll probably say both. They change every time the program is run, and they can only be resolved at runtime. So, loader's responsible for those. Assembler knows stuff about things within sections. The linker knows about stuff within the entire ELF file, and the loader knows actual addresses at runtime. Let's talk about the GOT. We talked about this last time. Quick refresher. The global offset table is a well-known jump table. It holds the addresses of functions or data that can be patched using relocations. The idea is we will make the GOT not executable but writable, so then we can patch it. We'll make the code not writable but executable, and we'll try not to patch it. We're patching the GOT instead of messing with the code. Okay? And the idea is, since the address of the GOT is a well-known symbol, we can get that and then get all of our things relative to this one absolute address, and then we're good. The problem is going to turn out to be that it doesn't, that we have an issue with finding the address of the GOT. But for right now, let's work through these really quickly as a refresher. Here we're getting the address of the global offset table as an external symbol, and it is in fact defined in the symbol table. We're now going to do this message with respect to sim. Okay, that's going to put the distance from the global offset table to message in that register. So there it is. There's the distance from the address of the global offset table to the address of the thing, and we get it this way. And we can use code like you see here to make that work. So we load the global offset table's address into RBX. We then take RBX, we add the offset to the thing we want, in this case message, and then we go and get the contents there. Except that won't work, because message with respect to got off is a 32-bit offset, and we can't put 32-bit things inside square brackets. Dang it. So we need to break this into two, and so that's what we do. We save the offset in RDI, and now we can add RBX and RDI together inside the brackets. Right? This 0 extends this value and stores that in RDI. We can also do with respect to ... got. What that does is create a slot inside the got, and it gives us the distance from the global offset table to the slot that holds the address of the thing we actually want. A little bit of indirection going on here. And it does several things. First, when we use thing with respect ... got, it creates a slot in the got for the address of thing. That will be a patch later, a runtime patch, probably, that will put the address of thing at that slot in the got, which is fine. Got's not executable. So it'll put it in there. In addition, we have to replace this in the code with the actual distance here. So it creates a link time relocation for this value, right? The linker is going to lay out the got and the text section and whatever thing is going to lay those out in the file. And so it'll know what this distance is, and it can patch that at link time. And then at runtime, the loader can patch this address. So it also creates a runtime relocation for that. So now we can call things like puts via the got. So when we do this right here, we will create a link time relocation to replace puts with respect to got with the actual distance from the start of the got to the slot we want. And we will create a runtime relocation inside the got for the address of puts. And there we go. We can see how all this works. If we look at this, we'll see we have 3 relocations. We have one for the global offset table address itself. We have then 2 others. We have this one in data, and then this one for puts. This one is for message, which is the start of data, and this one's for the address of puts. We link, and we take a look inside the linker, and we see some interesting stuff going on here. There's a relocation for puts. This is inside the got. Are we sure? Well, 3FD8. If we look and see where the got is, look in the section table, we'll see that got starts at 3FB8 and runs for 48 hex bytes. So yeah, that's inside that address space. So yes, this address of puts in glibc2 is a runtime relocation inside the got. That's great. But what is that? That kind of looks weird. And where is it? Well, it turns out it's at 1136, and 1136 is inside the text section. It begins at 1040 and it runs for hex 195 bytes. We have a relocation inside the text section. We didn't want that. We have a runtime relocation in the text section. We're patching the read-only bytes at runtime. We didn't want to do that. That was the whole purpose of having the got. What is this? It turns out this is for the got address, right? It turns out global offset table we've been just happily using as if it were a well-known constant. That is actually specifying an absolute address which is only known at runtime. Oh no! Oh no. This breaks our whole model. The whole reason we went down this road was so we wouldn't have to patch it, and we still have to patch it because we don't know what the address of the global offset table is. Well, let's go back for a moment and let's think a little bit harder about who knows what and when, because we have to figure out a way around this problem, right? We have to have an absolute address for the GOT, then everything else will work. So here's a question. How can your code figure out what its address is at runtime? Let's try that. So here's one possibility. I've got this piece of code that's get address, and what it does is it just goes ahead and does a load effective address, takes its address, puts it in RAX, and returns it. Shouldn't that work? Well, that will create a runtime relocation in the text file right here. And we don't want that. But, what if we did this? So take a look at this. We push RVP, move RSP and RVP, standard boilerplate, and then I do this. I say call get underscore RIP. Where is that located? Right there. So what do? I call this address. I call the next instruction. A call pushes the value of RIP onto the stack. The value of RIP, when I'm at the call here, is actually this address right here. So it's the address of get RIP. And that puts that straight onto the stack. Right? Sure. So that means that when I do the next thing, which is pop RAX, I actually now have in RAX the address of get RIP. The actual runtime absolute address of get RIP. If I want to know what get address is, I can subtract this distance. That is get RIP minus get address. Now, the assembler knows what this is. These are two locations inside the same section. So it knows this distance. And I was able to get this absolute address at runtime with this call pop trick. So this will get the address of get ADDR, put it in RAX, and return it. And there are no relocations in this. Nothing has to be relocated, because instead of trying to plug in a real value, I use this call pop trick to get one absolute real runtime address, and then I leverage that distance stuff to figure out the other one. That's interesting. Alright, so the assembler lays out the bytes in each section so it knows the offsets within a section. The linker lays out the sections and segments so it knows the offsets between segments. The loader moves code into memory with the actual VMAs. Well, we know a few other things. We know that the $ is used by NASM as a token indicating the current position in the assembly. And you've seen it being used. We saw it being used to take $ minus MSG. Right? So we have a message, bonjour monde, and then the current address is the first byte following that. And so if we subtract from that message, we get the length of this piece of this string. Now the assembler doesn't know the address following it, and it doesn't know the address of message, but it does know the difference between the two, and so we're able to make that work. Are there other tokens like $? Yes. $, for example, is the start of the current section. Now we don't know that address until runtime, but we can know offsets from the start of the section to other things in the same section at assembly time, and to other things in other sections at link time. That's interesting. Let's see what this might mean. How could we use this? Is there a way to do this? Well, it turns out there is another use of WRT we haven't talked about yet. And that is to get this sort of weird distance. So global offset table with respect to .PC creates a link time relocation for this signed 32-bit difference. Global offset table minus $. What is that? Well, global offset table is the absolute address of the global offset table. $$ is the absolute address of the text, sort of the text section. Since we're referring to it from inside text, if we're referring to $$ from inside data, it would be the absolute value of the start of the data section. So that can change. But what this is going to give us is the distance between the global offset table and the start of the current section. Okay. If we knew either one of those addresses, we could get the other one. Right? See what I'm saying? If I knew the absolute address at the start of the text section, I could get the address of the global offset table. If I knew the address of the global offset table, I could get the address of the text section by using that global offset table with respect to GOT-BC, by using that offset. Can I know either one of those? Well, if I can do global offset table, I'd be done. So that's not the answer. But maybe I can figure out $. And once I have that, then I can use this offset to get the address of the global offset table. So here's what I know so far. Okay, so suppose, just bear with me here for a moment. Over on the left-hand side are absolute addresses, things that I don't know. Right, the address of get RIP, $, and the address of the global offset table. I don't know these addresses. Over on the right are some distances that I can know. Right? I can know get RIP minus $, because the assembler will know that. That's inside a section. And I can know this because the linker will know that. That can be resolved at link time. Let's see how this all fits together. Absolute addresses not known until runtime. Offsets known either at assembly or linking. The assembler knows this offset because they occur in the same section of code and it doesn't change. The linker knows this offset because it lays out the GOT and the text in relation to each other, and that doesn't change. The value of get RIP can be found at runtime using that call pop trick. So follow the math here. If I know the absolute value for get RIP, I know the distance to the start of the section, and I know the distance from the start of the section to the GOT, I can now work out from that the address of the global offset table. Here's what that looks like. I figure out get RIP, then I add that distance, $, minus get RIP, and then I add this distance, right, from $, to the GOT. If I do a little bit of math with this, I can replace this thing with GOT minus $. And so now I have this expression. I can write it like this. The $, drops out. The get RIP drops out. And it's just the address of the GOT. So sure enough, that works. That is just going to be the address of the global offset table. And this is how you get it. And I'm not kidding. You can Google this. This looks crazy. It looks insane. It's really what you do. So what does that look like in code? It looks like what we have over here. I come in here, push RBX. I call getGOT. That's right here. And then I pop it. That gives me the address of .getGOT. And then I add to it this thing over here. Now, the linker knows what this is. It knows this number. It doesn't know what this is. It doesn't know what this is, but it knows this because it computes it, and it knows these differences. So it can figure that out and put in the correct offset to adjust from getGOT to the global offset table's address. And now, after I execute this, RBX holds the address of the global offset table. This math all gets resolved and filled in. Really, it really does. I'm not kidding. this line is this first line right here, right? It's get RIP, which is in RBX, plus $$ minus get RIP, right? Plus got with respect to got PC. And there you go. It's this thing. You can read on down through here and eventually convince yourself of this, and you should. So then we're going to use the got, which is in RBX, and so up here at the top we save it, and down here at the bottom we restore it. Wow. This results in a single link time relocation of this type right here, which is set up just for this case. So now we go back to our Hola Mundo program and we can make these changes. So I use the trick to get the address of the got into RBX. I use the offset of message to the got in order to get the address of message. I use the slot in the got for the address of putS to get the address of putS at runtime. I call it. There it is. I can assemble it. I can link it. I get a dynamic executable which has no relocations in the text section. Exactly what I wanted. This is how it works. That's how you build a dynamic, position independent executable. Done. You may be thinking that's crazy, but if you look in especially old 32-bit code, you'll see these get PC thunks. And typically you'll see several of them. Like this one is here. What is it doing? What is this guy doing? Why is it using move to get the value off the stack? Well, the idea is you would call this. So when you call it, that pushes your address onto the stack. This gets the address off the stack without popping the stack, so it can then return back. And so when you call this, the result that comes back to you in EAX is, this is 32-bit code, is your address, the address of the line that called it. And sometimes you'll see several of these in 32-bit code for returning it in different registers. So this is thunk AX. You might also see thunk BX and CX and DX to get this stuff into different registers in case you're using EX for something else. Wow. Let's talk about dynamic linkage. So our code has no relocations in the text section. We wanted that. Text section does not change. It doesn't need one for the got, but it still has to figure out where putS is located. And that's not in our ELF file unless we statically link it. And it's not relative to anything else, so we can't know until runtime. How does that part get fixed? So here's a statically compiled program, static Hola. That's what it looks like. Here's our dynamically compiled program, dynamic Hola, and you'll see that it has something the previous one didn't. It has this thing that says interpreter, and the interpreter is /lib64 /ld linux x86 64 so2. What? That looks like a shared library, right? A shared object? What is that thing? Well, that is the actual program loader. You can call it the dynamic linker, the program interpreter, I don't care. It's responsible for running other programs. And it's an executable. You can run it with no arguments and it'll print out some help information. So on my system, it's a symlink to another piece of code. And this thing lives in this weird in-between space because it has to be statically linked, but it also has to provide dynamic linking. It has to be statically linked because it's not going to load itself, and who's going to do it? So, if we take a look at it with file, it will say it's dynamically linked. If we take a look at it with LDD, it will say it's statically linked. That's interesting. It does some stuff. Namely, it gets loaded first. Then it loads any required shared libraries and maps them in the process space. It fixes up any remaining dynamic relocations in our code, and then it transfers control to our code's entry point. In other words, if you start a dynamically linked program in GDB and you use start I, you will find yourself at _start for the dynamic linker, not for your code. So you need to then continue and get to your code, which would be a second _start. You can use this to run other programs regardless of the executable flag. You can try that. If you do something crazy, like say you mark chmod as not executable, this will let you fix that, because then you can run chmod whether it's marked executable or not. It's also how LDD works. If you've ever used LDD to see the libraries that are dynamically linked in a program, it turns out LDD is actually a script that runs the dynamic linker. And that's great. It also lets you specify the library search path. That's a little problematic. I say that last part can be fun. It's fun in the sense that you can mess around with stuff. Suppose someone has admin privileges, and suppose they can add an alias to their shell. Then you can have just general mayhem by changing this system to, instead of picking up the regular libraries, pick up some malicious libraries somewhere else. Redefine some basic stuff. Can you really do that? Of course you can. So here's a little aside. Over on the right hand side, I have my own puts function, myputs.c. And you'll see what it does, right? It takes a constant char buffer, it ignores the buffer, and instead it writes out salamudunia. And that's all it does. So if I compile my Hello World or my Hola Mundo program with this, and it calls puts, it will find this puts first, and it will write out the wrong thing. I can make your code do anything by overriding the standard functions. The way I do this is I specify that my puts should be preloaded, and since it's loaded before any of the other libraries, my puts gets called first. Everything else will work just fine, but when you look for puts, you'll find mine first. So, runtime dynamic linkage. Our assembled and linked program still has a relocation for puts. If we look down there, we'll see, sure enough, there it is. 3FD8 needs to be patched to have the address of puts. So that's the virtual address affected by the relocation, and it's in the GOT. And right, we're going to figure out what that is at runtime. It'll be that offset from it. And so we need to patch the GOT at runtime. This specifies the symbol. It's symbol 2. And in fact, if you look in user include Linux elf.h, you'll actually see that that's how we extract it, right? We give it the info piece. We then shift it to the right 32 bits. 32 bits is 4 bytes. So we go 1, 2, 3, 4, and that means we leave those last 2 bytes and we get 2. And it turns out, if we look in the symbol table, 2 is puts at glibc 225. And there's the symbol table entry for it, in case you didn't believe. One of the dynamic libraries has to provide that. So if we do an LDD, we see what libraries it's finding, and we don't have our preload thing in the mix, we'll find out that we have Linux VDSO, libc, and LD Linux x86 64SO. What are all those things? VDSO is the dynamic share. We'll talk about it when we talk about. Probably when we talk about the stack, we'll talk about it. For a weird reason. It's a way to access kernel stuff. libc is a standard C library, and then that last thing is, of course, the dynamic loader. The likely culprit to have puts in it is libc. And so the numbers you see there are the virtual memory addresses of the loaded libraries. And they're going to change each time you do that because we have memory randomization turned on. So you can turn that off, and here's how you turn that off. So let's see what's in libc. So we can do that by looking at the symbol table for libc, and we can grep for puts, and we'll find it. So there's an fputs and some other stuff, but here we found puts right here. There you go. It's at 875A0. It's going to get relocated, so only the dynamic loader is going to know the final address, but it will know. And then it can fix the dynamic relocation in the GOT with the correct address of puts. All right. Now, we can also do the linking without going through GCC. Over on the right hand side, it's basically our Hola Mundo program again, except there's no main function. We have an underscore start. So I'm not going to call GCC to call the linker for me. I'm going to set up things myself to make this work. And up in that top line, you can see what's happening. So there's the make AS to assemble it, but then I call LD to link it. That's the system linker. I want the output file to be the base name of it. I then say -dynamic -linker, and I give the dynamic linker I want to use. I could use something else there, right? But I'm going to use that one. Then I give it the files I want to link, which in this case is just the object file with the C runtime. -LC includes the C runtime. And then I'm done. If you're writing a script and you want to use the make line for it, you can actually abbreviate all of that to this right here. Make dyne, and you might want to include the C library if you need it. All right. That was how we used to do stuff. AMD 64 made things a lot better. You probably won't have to worry about the GOT again. The GOT's still there. It's still being used. It still has relocations for it. Still works the same way it worked. Okay? But there were some issues with it. There's a notion that the GOT can get hijacked. If you go and look for that, you'll find it. And it was unwieldy, right? You could see that previous code was kind of annoying. I had that weird adding, subtracting thing going on, and then you have to keep it in the register, and it's just very annoying. So if you want to call something, you've got to either have that in the register passed to you, or you've got to recompute that. It's pretty bad. So a takeaway from this is a complex procedure is going to involve many interactions. Each of these can provide a vulnerability. So I can get a vulnerability by messing with the linker's preload. I could potentially create my own program loader and trick you into using that, finding that and linking with that. A number of ways I can get into some mischief with this. All right. Let's go back and talk about relative addressing. We've already seen this a little bit, but if we look at the code over at right, we've added a switch to the link line, and that switch is pi. I want the linker to make delicious, dynamic, position-independent executable for me. And that will be great. So what Hejverden does is we get the address of the GOT, we get format with respect to the GOT, we get underscore start with respect to the GOT, we get printf with respect to GOT, and then once I have all that, I zero out EAX, and then I call RBX plus R9. What is that? That's printf. Well, what are the arguments to printf? Well, they're in RDI and RSI, and they're the dot format string and the address of start. And the format is Hejverden with a hex address. So this will print out the address of start. And so I run it once and get this, I run it again and get this, because the location of start is changing because of address space layout randomization. But you'll notice, because it's a position independent executable, it's getting moved around in memory, and I'm still able to get the address at runtime, and everything works just fine because I'm making use of the GOT. Wow, isn't that great? Now, this might feel like overkill. So the address from .format to the code that loads the address of .format into RDI doesn't change, and neither does the distance from _start to the code that loads start into RSI. Be clear about what I'm saying. So this distance, the distance that from where I want to load this to the thing I want to load, I could determine that at link time, right? That's some offset, and the linker would know that. I just need a way to tell the linker to put that offset in here, but that's not good enough. There's not a move that gets things by an offset like that. Or is there? Well, there wasn't really in the 32-bit world, but in the 64-bit world there is, and it's RIP relative addressing. And here's what we'd like to do. I'd like to do that. I'd like to just say, I want to put the address of format into RDI and the address of start into RSI with LEA. Just do that. And and maybe do that relative in some way. If I try that with the PI switch, it'll say relocation against .data cannot be used when making a PI object recompile with -f pi. Well, I have pi already specified. Again, that's never going to solve the problem. This won't work. But I'd like it to work. Well, the AMD extensions added RIP relative addressing to a lot of places to solve this problem. And the idea is, at link time the code is scanned and offsets to locations that the linker can figure out are fixed up to reference data and instructions relative to RIP. So we've seen this a little bit already. This makes these references position independent. So here's what you write. You write load effective address into RSI of rel stir. The assembler generates LEA RSI RIP plus 0 because it doesn't know what that offset is yet. And so it puts zeros there, and it puts a special relocation pointing to these zeros so that the linker can patch it. Okay? The linker then fills in the relocation, so now it looks something like this maybe. LEA RSI RIP plus a particular fixed offset to somewhere inside the ELF file once it's laid out the sections. But it doesn't know and doesn't need to know the actual VMAs, right? I just need to know one real address, and then the offset to that I'll add or subtract will give me the final real address of the thing I want. And in this case, the real address that I know is RIP. Right, because I know that at runtime, and then I add this offset. Our code can now be position independent. This is so useful that if you want everything to be done that way, you can just write default rel at the top of your file. So RIP relative, we have to keep in mind that RIP always points to the next instruction. So RIP relative addressing adds a signed 32-bit offset to the address of the next instruction. So here, for this offset right here, 2E Charlie 7 is relative to this 1149, which is where RIP is pointing. There's that 32-bit signed little Indian offset. There's the value of RIP. We add them together, and compresto, we get a target, in this case, 4010. This is a way of referring to that specific address. And note, if we move this around, if we change this number, that changes this number, right? This is always going to be 7 bytes. So that's going to, we move these around, the 7 bytes are still 7 bytes. I'll still add this to it, and this will get a different number, but it'll point to the right place. Things aren't moving relative to each other, but they're moving in memory, all fixed together. So that brings us back to RIP relative addressing. So I replace those two lines that we're using the global offset table with those, with rel.format and rel.start. This says create RIP relative entries for these two. And that works. That will work. This code over here will still compile to position independent executable. Life is good. The challenge is I'd like to use the same kind of thing for something like printf. I'm still got to use the GOT because I still have to get printf with respect to the GOT. If there were just a way to use RIP relative addressing to avoid having to do that, how could I do that? Use RIP relative addressing to avoid that. Well, maybe what I would do, maybe I could load R9 with a RIP relative reference to the GOT entry that holds the address of printf. Got it. See, that would be great. So what I need to do now is say rel and then somehow specify the location in the GOT that holds printf, and then I'd be good, but I might still need to know the GOT to do that. Ugh, this is painful. Could I do that? It turns out, yes, I can absolutely do that. So up here, I say rel global offset table. That's going to be filled in by the linker. The linker doesn't know the address of the global offset table. It still doesn't know that, but it does know the offset to it because it's laid everything out, and that will work. So RBX now holds the real address at runtime of the global offset table, and everything else will just work. That's great. That's so much simpler. Life is good. We can stop there. Or maybe not. Let's think about this a little more. RIP relative addressing is great. It makes the GOT much easier to use, but we still have to have the GOT. Maybe there's a better way. What if we solved our table problem by creating another table? That sounds like a good idea, right? So imagine, if you will, we want to use RIP relative addressing for procedure calls. The problem is we don't know the address of the procedures that we want to call. We don't want to modify the read-only text section. So how about this? We create a table called the procedure linkage table, and it's close to the code. It's within a assigned 32-bit offset of the code. So I can reach the procedure linkage table using RIP relative addressing. And I populate that with code like you see right there. So here you see I'm jumping rel to puts at got.plt. What is all that? What's going on here? Am I saying I want to patch the PLT? No, I don't want to do that because the PLT is executable. If it's going to contain jumps, it's going to be executable, and I don't want to be patching it then. But what it is going to do is it's going to be an RIP relative reference that jumps to the address stored in the GOT for puts. All right, so follow me with this for a bit. There's a slot in the GOT for puts, just as before. It's patched at runtime to put the address of puts in the global offset table. But instead of us using the global offset table directly, the linker fills in the PLT entry. So that jump is followed by a relocation that points to that entry in the global offset table. Notice the square brackets. So we're jumping to the address stored there. And we're using RIP relative addressing to do it. So, if you followed all that, here's what we're going to do. Instead of our code calling puts directly, we will call puts at PLT and we'll use rel to do it. So it'll be an RIP relative call to puts at PLT, which is an instruction in the PLT which jumps to the address that is stored in the GOT for PLT. For puts. And then puts runs. Wow. That'll work because we call this thing in the PLT. It jumps, so when that returns, it actually comes back to us. Oh. So who's responsible for filling in the GOT? The dynamic linker. Now in the 64-bit world, this happens before your underscore start is called. The dynamic linker starts up. It patches all the runtime stuff. Then it invokes your process's start. We call this eager binding, and it's required by something called relocation read-only, which is a security feature of modern Linux. Relocation read-only says resolve all the relocations right now before you run the user's code. When you're done fixing the GOT, mark the GOT's pages as read-only so they can't be patched at runtime. And that prevents GOT hijacking, if you looked that up from last time. Whew. Oh, wait, you want to modify the GOT at runtime? You can turn that off. You can link with relocation read-only disabled. That's -z, no relro if you're using LD. If you're trying to do it from GCC, you have to use this cryptic way of passing a switch to the linker, -WL, -z, no relro. Phew. Do you want to know if it's enabled? You can use something called checksec. So sudo apt install checksec will install it. This actually checks the security features of a particular executable, and so then we can run checksec and give it a file, and it will tell us about it. Okay. Whew. Now, resolving all that stuff up front, eager binding, has an alternative, and the alternative is lazy binding. Under lazy binding, we don't resolve the address until the first time a procedure is called. How does that work? Well, we have to think about all this. And I'll mention here at the end, the PLT is created and placed in the ELF file by the linker. So that's where that comes from, in case you're wondering who creates the PLT. The linker creates the GOT. It's a table that didn't have any information in it initially. It'll be filled in by the runtime system. It creates the PLT and populates it, because the PLT is going to be full of little relocations that can be resolved at link time. And then everything else is done with RIP relative offsets. Whew. This takes us to another use for WRT. This is the last one I'm going to hit you with. And it's WRT ... Let me see if I can explain this without causing your brain to explode. When I say puts with respect to ... .plt, this creates a link time relocation for the 32-bit difference between what the RIP should be at that location and the slot in the PLT for puts. Alright, let's see what that looks like. So up here in my text section, I say call rel puts at PLT, or I say this, put S with respect to PLT, and that creates this jump instruction in the PLT along with a runtime relocation. I said that wrong. This creates this jump instruction along with a link time relocation, a link time relocation that points to this slot in the GOT that holds a runtime relocation for the address of put S, which is actually in another file. Whew. So, in the text, there is a link time relocation here that points to this code, which has a link time relocation here, which is a runtime relocation pointing here. So when I call it, I actually call this code, which jumps to here. The address stored here jumps down to there. Whew. This is good because now we don't have to get the GOT address at all. We don't have to fool with computing offsets. We just call the procedure and the assembler replaces this with the RIP relative call to the PLT and creates the appropriate relocation. The linker then fixes that up and we're good. Right? The assembler creates link time relocation records for the RIP relative call instruction pointing to put S. Doesn't know how the linker will be invoked. That's fine. The linker creates the PLT. Since it knows the relative layout of the program, it can fully populate it. The linker resolves the link time relocation from the assembler by pointing it to the correct PLT entry, and then the linker creates a runtime relocation in the GOT for the address of put S. So, with eager binding, here's what happens. The dynamic linker starts, it resolves the runtime relocation, it puts the 8-byte address of put S in the GOT slot. The dynamic linker jumps to the program entry point. When the call is reached, the processor pushes RIP onto the stack, loads the address put S at PLT into RIP. That causes the indirect jump that's stored in the PLT to happen, so it jumps to put S at GOT. It jumps to the address that's stored in the GOT slot. The processor loads the 8-byte address of put S from the memory in the GOT, and execution continues from there. The put S routine runs, it hits its return instruction, that pulls the address off the top of the stack, which is back where we started, and we return where we were to the instruction following the original call. What does that look like? It looks like that. So, after all that explanation, all that complexity behind the scenes, all that stuff still going on, relocations, stuff in the GOT, stuff in the PLT, runtime stuff, all that stuff is still happening. But the interface to you, the programmer, is now finally, mercifully, simple. That's what you do. You don't have to go and get the GOT or even think about all the other addresses. You just say, I want to call printf with respect to the PLT. And the assembler knows what to do, the linker knows what to do, the loader knows what to do, and it's all just going to happen. Still got to declare printf as external, but that's all you need to do. So notice how clean this code is now. I go ahead and load the format. I use rel to get to it. I put that in RDI. I use rel to get to start. Put that in RSI. I zero out EAX. Then I call printf with respect to the GOT. And I'm done. And I can build a position independent file. It's dynamically linked. Super small. Relocate in memory. And life is good. Now, the underlying process got way more complicated, even though our interface to it got much simpler. That complexity didn't go away, it's just hidden. The GOT is still there. We know that because we wrote code using it. The GOT's still there, all that stuff is still there. All that complexity is still behind the scenes. Whew. That was a lot to get through. Let's switch to something a little bit lighter. Let's switch to talking about calling convention, strings, and loops. The AMD64 calling convention. So I thought I'd give you an example that shows a lot of the pieces of this. So here's a little function that takes a lot of arguments. How many does it take? It takes 1, 2, 3, 4, 5, 6, 7, 8, 9 arguments. Some of these are floating point, some of them are integer, of a couple different types. And what we're going to do is we're going to compute the sum of all the 32-bit integers. There's just two of them, so we add I1 and I3. There's I1, which is a U32, and there's I3, which is an int32. And we're going to store that in a signed sum. I'm going to compute the sum of the 64-bit integers. It's I2, 4, 5, 6, and 7. I'm going to compute the ratio of the two floating point numbers, so F1 divided by F2. I'm going to print out a bunch of stuff, and then I'm going to return I1. So, how are these arguments going to get passed? How is that going to work? Let's apply the calling convention. The calling convention tells me that the first argument's an RDI, if it's an integer or a pointer. The second one's an RSI, if it's an integer or a pointer. So sure enough, these first two are in fact that. So this will go in RDI, this will go in RSI. The third one though is a floating point, so it goes in the first floating point register XMM0. The next one we're back to an integer or a pointer, and the next register for integers and pointers is RDX, so that's where that goes. The next one's a double. The next floating point register is XMM1. The next one for an integer or pointer is RCX, then R8, then R9, and we've run out of registers. If the next one were a float, we'd be in good shape. We'd put it in XMM2, but it's not. This one has to go on the stack. All right. So now we need to think about how to get it once it's on the stack. So we need a main function to call our code, and here's our little extern thing. Here's our main function that's going to take some values to call it. So now you can actually build it and run it and play with it. Let's compile the code and see if we understand how it's been implemented. So here is the code for subfunc. Right? There it is. And here is what we know from the calling convention. We know that I1 is an EDI, I2 is RSI, I3, and we know these floating points are in XMM registers, and we know I7 is on the stack. So let's see what's going on. Maybe we can map all of that to what's going on. I'd like to know where I7 is in reality. So let's think. Here's the initial stack before the call. I push I7 because I need it to be on the stack for the call. Then I do the call. That's going to push RIP, the return address, onto the stack. Then I'm going to push RBX, because I do that in my code. And so now I7 is at RSP plus 16. So that's how I'm going to get it. Alright, so here we go. You can see, here's my code. I do, in fact, do the push RBX. Then I compute the ratio of the two floating point numbers, div SD. I do the ratio. This divides XMM0 by XMM1 and stores the result in XMM0. And now I add. And you see this RSP plus 10 or RSP plus 16, right? It's 10 hex, 16 decimal. Is that our friend I7? And we go on down through the rest of these. Well, let's see. If we do the back substitutions, we put it in static single assignment, we do the back substitutions, we get what we would expect. EDX1 is EDX 0 plus EDI1 is EDX, EDI. Those are the two 32-bit ones, and they're added. RCX, I add I2, I4, I5, I6, and I7. I2 is an RSI. I4 is an RCX. I5 is an R8. I6 is an R9. And I7 was in RSP plus 16. That's it right here. And then I do that, and I compute the ratio. So there you go. You might be curious about that underscore printf underscore check at PLT. We didn't call that. We never called that. What is that? Turns out there's this thing out in the library. If you look at how printf is implemented, you'll find it's actually implemented to call printf underscore check. The first argument is a flag that indicates a level of checking, and this is a way of having it check the stack before it runs. So basically it's just printf. If you're curious about it, the header file's shown down at the bottom. You can go take a look at it. So then we return the values back. So this sort of shows you how all that works out, how all those pieces fit together. And this shows the arguments that go to, for example, printf underscore check, and how they're all laid out. You can examine that at your leisure. So that gives you a better sense, maybe, of how the calling convention works. It's not that way for every platform. The nice thing about Linux is the third integer value can go in the third register, even if there's other stuff being used. It's not true on Windows. If you miss your opportunity to use a register for a value, you lose the opportunity to use that register for that value. It's a very different type of calling convention. Let's talk about strings and loops. So there are some instructions that we haven't talked about much before. JRCXZ, JECXZ, and JCXZ. What are we doing here? They start with J, so whenever they're a jump. They're not JMP, so they must be conditional jumps. And if you look at it for a minute, you'll realize there's RCX, ECX, and CX in there. That's a register. Those are parts of that register of RCX, right? It's the 64-bit register, the 32-bit, and the 16-bit view of that register. And then Z is probably 0. This is jump if the content of RCX or the first 32 bits of RCX, ECX, or the first 16 bits, CX, is 0. This is a way of testing that register, and only that register, and then jumping based on that. There's not a version for RAX, there's not a version for RBX, only RCX. It's a special one. So I did a quick search through everything in user bin, and I found that it was used in BusyBox, Blender, Pandoc, rclone, and nothing else. So it's not widely used by compilers, but it is in fact used. I looked in BusyBox and did some disassembly to see where it's being used, and it's used to signal whether to take a particular branch in the subroutine, unsurprisingly. Let's talk about loop. So we've seen loop. Basically what loop does is every time it's encountered, it decrements RCX, and if it's not 0, it jumps to the specified label, or it jumps to the specified, uses the memory offset, same as any other conditional branch. The difference is, I can't just replace it with dec RCX and jump not 0, because dec RCX sets flags, and loop doesn't set any flags. So, take a look at that little piece of code over there. What's the exit value for this program? Right? What's going to be put into RDI at the end of all this? Well, up here, I compare RCX was 76. Is that going to be true? No, because right above it, I set RCX equal to FFFF. So this comparison is not going to be 0. So the 0 flag will be clear. Move doesn't set it, and loop doesn't set it. So when I get here, after the loop runs, after all this stuff, when I get here, the flags are still set according to this compare up here. And this says CMove Z. What is CMove Z? That's a conditional move if the 0 flag is set. We know it's not set, so that move doesn't happen. So RDI is going to contain the last value that was put in it, which if we look up here is 100. So RDI holds 100, and that's going to be the return value from the whole thing. This illustrates that sometimes setting the flags can occur far from where they're used. And you can use this to create some fairly obscure behavior in programs. There's other versions of loop, loop E and loop NE. Those are synonyms for loop Z and loop NZ, right? Equal and 0, same thing, right? This is loop if equal, loop if 0, loop if not equal, loop if not 0. And again, those are synonyms. So these are different versions of the loop, and they terminate when RCX reaches 0, just like before, but they can terminate early by testing the 0 flag. Okay, they're still going to decrement RCX and then branch if it's not 0, right? But they will also test RCX and test ZF as well. So in the code over here, the loop terminates early. When RCX reaches 7, this comparison will result in 0, and this loop NE won't branch, will fall through and go out. So RCX did not reach 0 for that. We terminated early. Okay, so this will always decrement RCX. So here we compare RCX to 7. It is 7, let's say. So that means that we're going to terminate the loop, but loop instructions always decrement RCX. So right after this loop instruction, RCX will have the value 6, which will get put in RDI and be returned. So the return value from this code will be 6. Here's a little bit different one. I compare RCX to -7. We start at 10. We're going to count down. We're going to hit 0 before we hit -7. So when I get done with this, RCX will be 0. 0 you put in RDI. The return value will be 0. There you go. Are these used? Well, they're not super common. I did a quick search. I found loop E in 21 executables. They included sudo, sudo replay, blender, and transmission. I looked for loop Z. I didn't find any. Probably because the disassembler emits loop E instead. Remember, they're synonyms, and the disassembler is going to not emit both, so I failed on that. There's no reason to actually count this. How about loop NE? I found one instance of it in Pandoc. I thought I had a second one, but I didn't. So that's where that left that comma in. How about loop NZ? Didn't find any. Anything that looks like loop. I found 109 total. Loop's not that common. There are string instructions. These are instructions that do something with a block of bytes. You can move strings, compare strings, scan them for a byte, a word, a double word, or a quad word. You can load from a string or store to a string. Now, think about moving memory. Think about taking a chunk of memory and moving it over by 1 byte. If you copy from the first byte, you will then overwrite the second byte, right? So you won't be able to successfully copy. So if you want to copy that chunk of memory over 1 byte, you should start from the end, and everything will work. Or if you want to copy it backwards a byte, now you'd start from the beginning to make it work. So the direction in which you go is important, and that is set by the direction flag. So the direction flag controls the direction in which these string operations work. When it's 0, you'll increment. When it's 1, you'll decrement. How do I set the direction flag? You use std to set it and cld to clear it. The flag is commonly clear, but it's usually a good idea to set it if you need it to be something. You won't see this much in code because often you don't care about what the direction flag is. How common are these instructions? They're fairly common. They're pretty handy instructions to have around to copy strings or to check strings for a particular token, etc. There are also these repeat prefixes. These repeat a string instruction some number of times. They are not instructions themselves, they're just prefixes. And they work similarly to the way that loop stuff works. They repeat the subsequent string instruction the number of times specified in RCX, and they also have an early exit based on the 0 flag. This can help avoid branching. These are implicit loops. So here I put the address of stir in RSI, the address of pad in RDI. I load the string length into RCX, and then I say move. This copies the entire this length copies the entire string from here to here, and it does it all with this one instruction. Down here I load the string in pad, I load the address of pad into RDI. I load an exclamation mark into AL. Has to be AL. I load the length of the string into RCX, and I call scasb, and that gives me back the address of the first occurrence of an exclamation mark in that string. So, notice what's happening here. I don't specify any registers with these instructions. The source register is always RSI. The destination register is always RDI. The count's always RCX. If there's a character you're using, it's always AL. That's just how they work. So, first example is explained there. As it works, RSI and RDI get incremented or they get decremented depending on DI, and this gets decremented every time until it's 0. For the second one, we only need to use RDI, and it gets incremented each time. RCX gets decremented until we find this guy, or RCX hits 0, either one. Okay, all this is just pointing out the only way to learn assembly is to spend time reading, figuring it out, and especially writing assembly programs. You have to do both. You have to both read them and write them in order to get a really good intuitive understanding of what assembly is doing. And even then, it's going to be hard. Okay, it's not a language it's not a high-level language. You just have to accept it for what it is. That's it.